Definition of a directional derivative for, say, a function of two variables. You can talk about it for a function of two variables or a function of three variables. And if it's a function of two variables, then it would be in the direction of a two-component vector, and if it's a function of three variables, then you'd be thinking of it in the direction of a three-component vector. So the number of components of A has to match the number of variables, which will in turn give you the number of components in the gradient. So either way, it's gradient dotted with the vector divided by the magnitude of the vector. So it's the dot product of a gradient and a unit vector that's in the direction that you're specifying. So two-component gradient, two-component A, or three-component gradient, three-component A. So if you begin with the parameterized curve in the plane, like in this picture, any of these curves, square root x, or x to the 3/2, or what will give you a circle, which you could write parametrically using cosine and sine, radius times cosine, radius times sine, or, for example, y equal x, and there are lots more such things you could do. These are not the only curves you could think of. So you begin with something like that. Then you form the companion curve, which we've talked about. So I have the light green curve, and then its companion curve up on this surface is the darker green. So I'm using C for the curve in the plane and K for the corresponding companion curve. And then the subscripts match. So, for example, this first one, if I have it parameterized, if I change the letter, there wouldn't be anything mathematically wrong with just using the letter X as your parameter with limits on X, but the custom is to change to something like T if you're doing things parametrically, mainly just to emphasize that you have parameterized. So then T root T would be components of the vector, the tip of which traces a curve like this that would look like y equals square root of x, which you see opens over your x-axis, which is the black line back over here. Then the companion curve takes each point here, so that x and y are the same in the k, and then if you're on this sphere and on the top half, your z is square root, so puts this z with it, and that gets you points up here. So you'd have roughly a drawing like this. So then we think of arc length S of t, with t as this parameter for the parameterized curve, measured along this companion curve. And so that would have the same interpretation as in chapter 13, where we think of the curve like a road and the little car or the train engine, and the headlight of the train or the car pointing the direction to the tangent and velocity vector. All that's still the same kind of thought here as we're up here on the dark green curve, K1. So what we call the directional derivative then is equivalent to df ds, where f of xy, you see, is this, and the s is measured along the track or along the road, which by the chain rule is df dt over ds dt. So that's going to give you the slope of the companion curve. So it's the slope of the stick here as I'm holding it in the direction of the tangent to the corresponding curve in the lighter green down here. So I'm thinking of the other stick. I'm thinking of the direction pointed out by how I'm holding this stick, you see, which is lined up with my green T1 here, maybe you can see it. And then I have, going off in that direction, the tangent to the curve up here. And so they're going to intersect at an angle, and the angle back of my hand that has the watch on it would be the angle alpha, say, and tangent to that would be this directional derivative. It may be that I'd have better luck with the blue ones as far as being able to hold the stick. So I have a stick like this and a stick like that. And the only trouble, of course, is that I'm in your line of sight. But maybe you can see that there is an angle back here where I'm banging the sticks. Pardon me, I'm a frustrated musician, you see. Okay, so that's the idea of what we're getting at. So, for example, if you're thinking of the actual calculation, let's see, we've done that somewhere here. Well, I guess that's what I have here. So there are two ways then that you can get this directional derivative. According to what I have, you could do df dt and divide by ds dt, or you can do the dot product of the gradient with the a over the magnitude, where you're what I'm calling A over here would, for example, be T1 if I'm thinking of working with the green, or T2 if I'm working with the blue. So if I parameterize K, then my df ds, as it says here, is this quotient of derivatives. Or I can do the gradient dotted with the tangent over the magnitude. So if I'm thinking of curve C1 here, the R is T root T. And so I can do dr dt. Derivative is 1. Derivative of the square root is 1 over 2 root T. And then I can take the values at 1, 1, which is the point down here. And so that would be what I get when t is 1. So I get 1 and 1/2. So that's the dr dt. In other words, that's the t vector. And the ds dt is the magnitude. So you square this, that's 1. Square that, that's 1/4. 1 1/4 is 5 quarters. So then your ds dt is the square root of the dot product of this with itself, which is your 1 plus 1/4. So you get root 5 over 2, square root of 4. And then your two-component gradient using z equals f of xy for this picture. So using this function, 6 minus x squared minus y squared, half power, my gradient is partial with x, partial with y, and if you do the derivative, you remember chain rule, the derivative of the square root is 1 over twice the square root, and that square root is z. So you have 1 over 2z times by the derivative of what's under the square root sign, which is minus 2x. So your partial with x is minus x over z, and your partial with y is minus y over z. And then the x and the y are 1s, and the z is 2, so you get minus a half, minus a half. And so you see that gradient, like the brown here, is pointed at this particular point. It's pointed right square in toward the origin in my picture for the gradient and for this point 1, 1 out here. And so doing the directional derivative this way, which is what we're doing, we have gradient at our point, the unit tangent at our point as a vector divided by the length of the unit tangent. Well, so it isn't really a unit tangent, it's just the tangent and divided by the length. So this vector divided by that, that's the unit tangent. So your directional derivative is gradient times the unit vector in the direction you're talking about. And so if you work this out, you see you have minus a half, minus a quarter, so that's minus 3/4 over root 5 over 2, and then you invert and multiply, and you get this. So that number then would be the tangent of the angle that I was trying to indicate with the sticks that we're trying to get on this side. Maybe I'll have better luck with it. So what I'm talking about is something like this. The bottom stick is the line that your tangent T1 points out, and the top stick is the tangent line at the point up there to the green, dark green curve, and the number, the minus, where did it go? The minus 3 over 2 root 5 is the tangent, like in trig, of this angle that's down here. And so you can do arctangent of minus 3 over 2 root 5, and you can actually figure out how many degrees that is. You notice it's more than 90 degrees. Your tangent's negative. So you're coming around. So you got an angle like this. You're coming around from here to there. So that's more than 90 degrees. Well, I seem not to have very good turnout today, so I better get the names. Suppose you try it the other way. Suppose that you simply parameterize what is your f of xy, your z. And so that would be doing this. You see your z, again, is square root of 6 minus x squared minus y squared. So if you're on the green curve, then your x is t, and your y is square root of t. So parameterized, then you would have 6 minus t squared minus square root squared. So that's a t, not squared, notice. And so then if you do df dt, like first semester calculus, you get 1 over twice the square root, which I hope everyone has memorized is the derivative of the square root function, times by, according to the chain rule, the square root of what's, or the derivative rather, of what was square rooted. And so that's minus 2t minus 1. Okay, and then you divide that by the same ds dt that we had up here. The magnitude of your direction vector here is ds dt. So again, the root 5 over 2. So if you work this out, you get the same number, which will always be true. So you can think of your directional derivative both ways. You can think of it that you have the function of t, which is your curve, as parameterized, which is what I'm calling k1 up here, and that it's simply the derivative of that over the ds dt, and that's this number, and that's the tangent of the angle I've been trying to show you. Or you can say it's the dot product of the gradient with some vector, not necessarily a unit vector, that's pointing your direction, divided by the length of that vector. So that in turn is to say that it's the dot product of the gradient with a unit vector in the direction you specified. And you get the same thing either way. So in terms of interpretation of what do you have when you do it, the gradient points in the direction of maximum rate of increase of whatever physical quantity you're thinking your function represents, that the graph of which function defines that surface. So it could be like temperature. You could have a source of heat, say, at the origin, and then these spheres would be surfaces where you have the same temperature. That's why people call them isotimic. Could be same temperature, same voltage, if it's electric potential, things like that. Same barometric pressure if you're thinking about weather patterns and so on. And so the gradient then points in the direction to go for maximum rate of increase, like degrees per centimeter. So you could be a mosquito in Florida flying madly to find somebody to bite the Zika virus and so on. And so you're homing in on the temperature where the person is, which is warmer, you see. And so you fly in the direction of the gradient, and if you're trying to get away fastest, go coolest fastest, it would be minus the direction of the gradient. So, as I say here, one direction gives warmest, fastest, 180 degrees opposite gets coolest, fastest. Okay, so if you're thinking of a surface then, defined by, say, this is the one that goes with the handout that we looked at last week that has the maple. It's the one where the sphere has radius 3 instead of radius square root of 6. getting all sorts of people here. See, I told you to keep your papers. And so, if you're thinking again of that one, that goes with the picture that's over here still. We have with that portion of the sphere which has radius 3, we're thinking of our parameterized curve along here, the line at y equals 1 parallel to the x-axis, and the companion curve is this one still on that surface. And then then we're thinking about what would be the slope of the tangent line to this companion curve at measured at some point that's the companion point to a point down here in the plane that we start with. So we start with the point where x is 2, y is 1, which is this point, and the companion point on this sphere, see the radius is 3 this time, is 2, 1, and 2. So what we have been saying is that our partial derivative with respect to x gives us the tangent of this angle alpha that I have here. So this is a special case of the directional derivative. So we have what I called slice A in the maple handout, which is that red colored curve up on the surface of the sphere. You see where the x is variable, the y is fixed, and then the z is what this gives when you have parameterized with t there and 1 there. So square root of 8 minus t squared essentially is getting the z's. So that's the companion curve for the c, where the c is the line parallel to the x-axis, which I was showing you is in the picture, and I was standing over there. So the curve c for this would be parameterized as r of t is t comma 1. The 1 is the y that's fixed, and I'm replacing x by t when I parameterize, which is what you do normally. So then at the companion point, again, your slope for the companion curve, which is this thing, would be gradient dot dr dt, dr dt from here over the magnitude. So the gradient, you see, since you're talking in the direction of a two-component vector, if this is two-component vector, then you have to take this in the two-component form, or else you can't do your dot product. If you're doing a dot product, the two vectors have to be the like number of components. Same idea as multiplying matrices. If you've ever worked with that in algebra at all, you have to be able to do the dot product, so the row length across from the left matrix has to be the column height from the right-hand matrix. If you haven't done that, then forget I said that. Okay, so our gradient dot and so on will be partial with x, partial with y, dot, 1, 0, which you see is the dr dt. The derivative of the t here is the 1, the derivative of the 1 is the 0, and that is actually a unit vector. So this is a 1 down here, and what it leaves you then is f sub x, partial with x, times 1. So what we're saying is that the directional derivative for a situation like this is just your partial with x. And that's what the point I was trying to make is that your partial derivatives with x and y are special cases of this directional derivative, which allows not just for curves in the xy plane like this one or the green one that are parallel to the x or y axes, but also allows for curvy curves, if you will, like these, that are not lines at all, and also for the curve being a line, like y equals x, but not limited to lines parallel to the x or y axis. So the directional derivative, which works for all this, works as a special case for the two partial derivatives that are where we started when I first put this picture on the board. So that's what I'm saying over here. Same game then for partial with respect to y. And so my conclusion that directional derivative is the generalized partial derivative. Now, if you think of this same sphere, the one with radius 3 this way, think of a function of 3 variables, say call it w of x, y, z, equal this, then when that function of 3 variables equals some fixed value, like 9, you have what people call a level surface or an isotemic surface. If this is temperature, for example, that spherical surface is where the temperature is 9 in whatever units it would be, no matter whether you're North Pole, South Pole, equator, what have you. So then the corresponding chain rule for the derivative with respect to t, dw dt, again would be gradient dot d capital R dt, and the capital R now would refer to tracing out a curve on the surface. So this would be for any curve k then, for which the tip of R of t traces k on the surface. So once again, if this is an isotemic surface so that the w is a constant, then the dw dt is derivative of 9, say, which is 0. So that says that your gradient dotted with the tangent to a curve up on the surface is derivative of 9, which is 0. So then the gradient is normal to the tangent of each such curve. You could say that is what you mean by saying it's the normal to the curve, or let's say you could put that in. Tangent of each such curve. So that gets us to a handout that most of you got yesterday, the one that says Math 275, section 14.5, normals to parameterized surface. That should have been plural surfaces, shouldn't it? And you see the picture, which is very much like this picture, with the green and the dark blue and the red here, and this one, which I have in purple on the board. I didn't have a purple pen, so you were not here, so you don't have it. And somebody who was here certainly managed to get here without it. So who's willing to admit you got here without this? Because we're going to look at it now. So you can't find it, let me give you one. Okay, everybody got one? Okay, so you see how the layout goes. It's very much like what I have here. I have my C1, C2, C3, and C4, and then the corresponding K1, like these, are the same. And then you see, if you're at t equal 1, derivatives of companion curves. So if you look at the companion curve, you see that's z, that's what's tracing out the curve. That's the capital R that's tracing out the curve, like the dark green, the K1. So the R then that I'm talking about when I talk about R1 is this 3-component vector. So you look at the bottom of the page and you see I've done the derivative. Derivative of t is the 1. See, it's the second line above the bottom of your page as I'm holding the paper. And then your derivative of square root of t is 1 over twice square root t. And then your derivative of this with the chain rule, you have twice the square root in the denominator, and then you have minus 2t minus 1 in the numerator. And then you evaluate all that at t equal 1, and you get the vector, as I say there, 1, 1/2, minus 3/4. And so that would be the T1 the way that I've shown it in the picture on the paper. If you notice on the paper, the T1, T2, and so on, they're vectors that are up here. So they are 3-component vectors. So they're not the same as what I have on the board, which are down here and are 2-component vectors. Okay, but they are, what I've written on the paper is consistent with what I've drawn in the picture on the paper. So these are the tangents then at this companion point, which is 1, 1, and 2. They are not necessarily unit vectors. You can see that 1, 1/2, and minus 3/4 isn't a unit vector, but it's a vector that's pointing. It would be up here. It would be T1 in the dark green, like that. So I guess I could do it that way. I'm saying now that dark green T1 is different critter from light green T1 in that it has a Z, non-zero Z component. So it would be a thing like this. Guess I won't put the line on it. Okay, so in that way, if you turn the page, you see I can also get the tangent, which would be dark blue and would be up here, T2, that would be the dr2 dt. And you see I have it there on the right-hand edge of your paper, 2, 3, and minus 10/4. And I can also get a T3. Now, with the level curve, which we're going to talk about next, down here, this is in a plane parallel to the one up here. So the T3 up here is the same as the T3 there. They're both horizontal. They're both in a horizontal plane, so they both have 0 for the third component. And then a level curve, which is what this is a special sort of situation which we're going to talk about in just next. Okay, so I can get these various tangents that are on the sheet of paper. So then if you try cross products, and I try various, I try 3 of them there, you see. If you take T1 cross T2, in other words, dr1 dt cross dr2 dt, and you work out the cross product as I have, see your answer there is I plus j plus 2k. It's 1, 1, 2. Okay? Keep that in mind. Take another cross product. Would be like T1 and T3. And look at your answer, and you have 3/4 I, 3/4 j, and 3/4 times 2, which is 3/2 k. In other words, the first cross product and the second one point alike. The second one is 3/4 of the first one, but they're pointed the same. And then look at the third cross product, which would be like T1 and T4. And you see that one is 1/4 of the T1, T2. So the point is that if you have these tangent vectors like T1 and T3, any of the possibilities, their cross product is going to give you the normal to the plane they're in, and that is the same thing as, in the case of the sphere, the r of t vector, which you see is the vector from the origin to the point, the vector 1, 1, 2. So all these cross products you could do are going to give you some vector that is a constant times the 1, 1, 2. For a sphere, and this is a special case for spheres and circles, and that's what I'm talking about here, the position vector that the tip of which defines the points on the surface of your sphere actually is normal to the sphere. It's true for a circle also, that the radius is perpendicular to the tangent of a circle. That's something that they prove geometrically in high school geometry, if you can think back that far. And it's easier really to prove it with calculus. So, for instance here, where I took my 3-component gradient, you see when I did the partial derivatives, partial of x, partial of y, partial of z, each time I bring a 2 down in the front. So my partial of x is 2x, partial of y is 2y, partial of z is 2z. So my gradient is twice the x, y, z, or r vector. It's twice the position vector. This is the same r vector like on the test on chapter 13 that some of you have done and some of you are doing, where the tip of the r vector is tracing out the curve. You see, this tip of this vector is tracing out the top hemisphere. Okay, so what we've proved is that the gradient is proportional to the r vector for the sphere. It's also true for a circle, but it's a special case. It's not true for other types of surfaces. The gradient for any type of surface points the normal, but the gradient generally is not just a multiple of the position vector. That's true when it's a sphere or a circle. And so if you take those tangents and do cross products, which certainly gets you a normal, you see each time you get the gradient back, or half the gradient, or 3/4 of it, or twice it, or something. So that's what I've written here, what I've been saying. Generally, the R for the surface or the R for the curve do not point normal to the tangents of the curve C or the surfaces. But it is true for circles and spheres. So now if you're on the sigma, if you use the position vector then, 2, 1, 2, for your normal. So now I'm here, and this is, let's see, the 2, 1, 2. No, that's this one. Okay. So my tangent plane and normal line are over here. So going back to this sphere, for instance, I have 2, 1, 2 as my point on the surface. It's also, if you put on angle brackets, it's also the vector R down here, since it's a sphere. And it's also the normal. So the line L then, the normal line, has 2, 1, 2 for the direction numbers, what we called L, the L vector in chapter 12 that gives you the direction. Also the 2, 1, 2 you see are the attitude numbers for the tangent plane. Remember, attitude, like you talk about spacecraft or an atomic submarine or an airplane, something with 3 degrees of freedom, like camber and caster and toe-in for the front end of a car, where you have 3 degrees of freedom. Attitude, you're using attitude numbers in that sense. So thinking of that picture over there, using the 2, 1, 2 for your normal, to get the normal line at this point, these numbers serve 2 roles. See, they're the coordinates of a point for this line that pierces the surface of the sphere at the point with these coordinates, and these also give you the direction numbers, the equivalent, the 3-dimensional equivalent of slope. So like chapter 12, your line from point 2, 1, 2 to x, y, z is defined by saying your vector from the given point to x, y, z is your parameter times, so proportional to your direction vector. So in this case, these numbers are the same numbers as those. So then your parametric form says x minus 2 is 2t, so you can solve for x. Y minus 1 is 1t, so you can solve for y. Z minus 2 is 2t, so you can solve for z. So this is the normal line in parametric form. I think all of you are smart enough to realize that what's the third test is going to be, which I'll give you next week, is going to be this kind of stuff. Give me the tangent plane, give me the normal line, and you're going to have a sphere, of course, because that's the only thing I can draw, right? And so on. So anyway, this also gives the attitude numbers for the tangent plane, and then these numbers now are the point in the plane. So we're talking about a plane that touches the sphere at this point, the line that is perpendicular to that plane that pierces the sphere at that point. Okay, so TP is tangent plane here. So then your vector in the plane from this fixed point to general point x, y, z is perpendicular to the normal, which is this vector. So the dot product is 0, and so you work that out. 2x minus 4 plus y minus 1 is there, plus 2 times z minus 2 is there, and then you can collect your terms, do your algebra. So we get tangent plane and normal line. So we have alternative computations of the normal to a surface. This would be true whether the surface is a sphere or not. If it is a sphere, of course, you can simply use the position vector, which we've talked about. But if you want something that works when it's not a sphere, then you'd think like this, that sigma is defined by z equals f of x, y. So you could rewrite that this way. Then you have, you see, a function involving the 3 variables, so you're thinking of it now like a level surface. W of x, y, z equals a constant. And then in that way you could use your 3-component gradient, or 3-variable gradient, because you have 3 variables. So your partial with z is 1, and then you have minus your partial with x. See, the minus sign is y that one, partial with x, and the minus sign is y partial with y. So thinking of this way, with 3 variables, your 3-variable gradient gives a normal to the surface. And you notice it's upward pointing because your z is plus 1. You could also have done it the other way, where it was f of x, y minus z, and that would point inward. But the custom is to focus on the upward pointing normal. And so if this is your f of x, y, then when you do your partial with x, as always, you're going to have 1 over twice the square root, which I'm calling z, times by the partial with respect to x of what's the inside function. So that's the minus 2x. And in the same way, your partial with y will give you minus y over z. So your gradient then would be of z minus f of x, y. According to the formula, your normal would be minus your partial with x, minus your partial with y, and 1. So for this particular sphere and this particular point, you'd get 2 over 2, which is 1. Notice it's plus. 1 over 2, and then 1. And you notice that's proportional to your position vector, which it should be because it's a sphere. So the normal using this general approach, minus partial with x, minus partial with y, and 1, is consistent in the case of a sphere with what you know it should be, which is some multiple of the position vector. So we've proved that. So this is a usable formula for the normal to a surface defined as z equals f of x, y, whether that surface is a sphere or not. Okay, and then this that I have here in the notes we talked about already. We looked at our sheet of paper and talked about the cross products of the tangents, and that you get a normal that way. So then the last thing to talk about is the tangent and normal for a level curve. So that is in here, and if you have really sharp eyes, you may notice that the brown line, x plus y equals 2, that I've drawn in here, wasn't there yesterday. Or so this last part is talking about the purple, if you think that color is purple, or violet if you think that color is violet. I'm not going to try and be true to my colors here, so I'm not going to try and argue what color that is. Anyhow, that's supposed to be the arc of a circle for which the radius is square root of 2, and it is what we call a level curve, because you see at all points that are in this color on the arc of the circle, x squared plus y squared is 2. So if you put that in here, you're always talking square root of 6 minus 2, which is 4. Square root of 4 is 2. So for every point down here in purple, the companion curve has the same z value. In drinking water? Well, that isn't too bad, is it? Okay. And so by a level curve, you mean the same thing as if you said contour. If you think of geology, say, a topographic map, and the contours represent curves such that you have the same elevation. Okay, so this contour is a curve such that your elevation, which is your z value, is square root of 6 minus 2, so it's height 2. So if you have a thing like that, then your gradient will be at right angles to your level curve, which we'll see, but it'll always be true. So on a contour map, if you're physically able to do it, climbing in the fastest way would be to be walking at right angles to the contour. Now, you may not be physically able to do it. There might be a big drop-off, or there might be a canyon full of poison oak, or all sorts of things, but in theory, that would be true. And so opposite to the gradient, which would come this way, like the stick is now, would be how to go downhill fastest. That may be physically more doable, but you may not like the experience if you land on your head on the way down, something like that. And at right angles then to your gradient will be your tangent line. And so that's what we're trying to explore here. So if I'm thinking of my picture there, again, my df dt is gradient dot dr dt, and it's going to be 0, you see, because if it's a level curve, I have a fixed function value, a fixed z, a fixed height, which in this case is 2. So this 0 is the derivative of 2 when you apply this. You see, when you do your gradient dot dr dt, you have this dot dr dt, and derivative of 2 is 0. This is your gradient for the function defined this way. I'm using z instead of square root of 6 minus x squared minus y squared. So if I'm thinking of this picture, and z is 2, then what I have is minus a half, because x and y are ones, and that's perpendicular then to the tangent, which is defined by the dr dt. That's the thing I've been calling T3 here, because they're perpendicular, because the dot product is 0. So since this is a level curve, then this companion curve is in a plane that's parallel to the xy plane, a horizontal plane at height z equal 2. So therefore, the T3 up here is the same as the one down here. It has its third component, 0. And so your T3, whichever one you're thinking of, would be what is the perpendicular to this vector. Well, remember in chapter 13 we said if you have a two-component vector, say A comma B, you can reverse the order and make one sign change. So either you have B comma minus A or minus B comma A, and that dot product is 0. So I'm playing that game here. So if I have this from the gradient, which would be the brown in the picture, then I can reverse the order and make one sign change, and the dot product of this and that will be 0. And the reason that I have it with the negative for the x and the positive for the y is to have the one that's pointing like I show it. You see, if you look at how I'm showing things, remember x comes out here, so it's pointing back, so that's negative for the x, and it's pointing off to the right as you're looking at the picture. So that's positive for the y. If I took the other normal, plus here and minus there, that would be pointed this way. It would be a normal to the gradient and would be a tangent, but if your parameterization is the way it normally would be, positive would be going around the way this points. See, I'm saying x is square root of 2 cosine and y is square root of 2 sine in my original parameterization. And so if you think of increasing t in the way that cosine and sine want to go, then you're going around counterclockwise if you were sitting up on the North Pole and looking at a clock down on the floor. So then I can say that this is the direction vector for this line, the same business as we were talking about over here in chapter 12 thinking. So I have a line then where the 1, 1 would be the point on the line, and the x minus 1 is minus a half t, and the y minus 1 is 1/2 t. And you notice if you added these two equations together, you'd get x minus 1 plus y minus 1 equals minus a half t plus a half t, which would be 0. And then if you simplify, you get x plus y equals 2. So simplified, the brown is x plus y equal 2. You see it isn't perfectly drawn because in my drawing I have 2 there and there. So this end of it is going through the 2, but it ought to be more like this, like I'm holding the stick. So my circle ought to be squashed in a little bit, but nobody ever said that I was supposed to be an artist. So I managed to prove every class that I'm not. Okay, now there's another way, this is the last breath here on this stuff, that you can get the tangent line here to your level curve, and that is to think about your parameterization. You're talking about, for the purple, the parameterized curve, √2 cosine, √2 sine. And so if you think about it that way, here's your r of t, so dr dt gives the tangent, doesn't it? So simply do dr dt, and you'd have your √2. From cosine you get minus the sine, from sine you get cosine. Then that continues over here, which was the only place I could find any room. So then the tangent to the purple curve there at pi over 4 is your dr dt at pi over 4, and sine and cosine are both square root of 2 over 2. So you have √2 times √2 over 2, so you have minus 1 comma 1. When you put in, get your values at pi over 4. So that's the same thing. Before, I took the normal and reversed the orders, and I had something that was pointing like minus a half, 1/2. Well, minus a half, 1/2, and minus 1, 1 are vectors pointing the same way, aren't they? I didn't claim either one of them was the unit tangent, you see. So I can use anything as a tangent that's pointed correctly. So I can use this vector for my tangent, and then, you see, what I have is I have a point, which is the 1, 1, and I have a vector that's pointing the direction of the tangent, minus 1, 1. So x minus 1 is t times the first component, y minus 1 is t times the second one. And then again, if I add them together, eliminate the parameter, I have the same thing. So two ways to get the same thing in xy form are the two things I did. Either get the gradient and say what you want is normal, so reverse the components, or simply say, well, your parameterization gives you r of t, so do dr dt to get your direction of your tangent. And once you have a point and the direction for the line to go, then you're in chapter 12. And if you eliminate the parameter, you see, you get the same thing. Parametrically, these look a little different because this is t, whereas back here we have half t. But that just means that to get the same graph, you have to go twice as far if you use this parameterization with your t values. As, in other words, if t is 0 to 1 in this parameterization, and it's 0 to 2 in that one, you trace out the same curve. So that isn't really a big deal. You do get that if you do things parametrically, that to get the same graph can depend on choosing different limits if you have different parameterizations. And that maybe is the dark side of doing things parametrically. Well, let's just take a look at our maple before we give up on this stuff. First of all, I have a handout that's kind of a summary of all this, or trying to be, in my handwriting, so let me offer you this, and if you think it's confusing, then don't read it. But I've tried, there's a lot of stuff here, if you think about everything I've been saying for a couple of weeks. And I've tried to put it all down on one sheet of paper, and not even on the big paper. If I put it on the big paper, I could get it on one side. Oops. So you may find that this helpful, and you may not. And if you don't, then don't worry with it. So then the other thing would be this maple handout. I thought we'd look at this maple handout a little bit. If you have looked through the maple handout with the picture, draw the normal line and the tangent plane, and the surfaces with the slices in them. In other words, I'm referring to this picture and to the maple handout that I think all of you have, that's several pages stapled, that has quite a bit of typing on the first page. And then I finally define square root of 9 minus x squared minus y squared. If you look through the rest of this, you find that I've used maple to draw the tangent plane and normal line. I'm not sure. Do you have this? Yes. Okay. I think everybody else does. Okay. So then with the one that I've just given, if you bring up the vector calculus package, you can use the commands. You see it has the command gradient. So problem 1 in 14.5, you type gradient, then the function y minus x, and you have to say, are you thinking Cartesian coordinates or something else? So it demands that you say xy or xyz. Even though you may think that it's obvious, don't argue with computers. That's when they lose your emails. And then you have to take responsibility, right? Okay, so you see that your partial with x would be -1. Remember that in this vector calculus package, the e sub x is the same thing as I, and the e sub y is the same thing as j, and the e sub z is the same as k. And so it's the same as if they had written it. Notice what I finally did, and with the subs, put in x equal 2, y equal 1, doesn't change anything in this case because your gradient was constant. But then if you type convert list, then you get to see it more the way you're used to seeing me write vectors. You have squarey brackets instead of angle brackets, but it's a way to see for sure what they mean. So then the next one, log, we do the gradient, I substitute the values, and then that's one. And then I've done 7 that way. And then you notice that with the next one down there, it's something that the computers didn't like, obviously. I'm not really sure what I did to displease His Majesty, but anyhow, you turn the page, and I have the directional derivative. So the command is directional diff, and you have your function, and you have to put in the function, and you have to take it in the direction of a vector. Your vector, this would be like my gradient dot A, and you don't have it to put in a unit vector. If you simply say the directional derivative, you give the function and you give the vector that would be the A, then it does the actual calculation with this formula, which is to do the gradient dot with the A and divide by the length of A. So you can give the command and the direction vector. You do have to say that you're working with Cartesian coordinates. And so 12 would be your dot product. Then if you want the directional derivative at a particular point for this function in the direction of that vector, then you do the subs for the x and the y values, and then you actually would get a number. You see, well, that would be like here, what you're getting finally as a number for the example here with the darker green slope. That would have been this minus 3 over 2 root 5 is the directional derivative number for this picture that we did. And so the minus 4 from formula 13 is the equivalent to that. And then I've done the same thing in problems 15 and 19. And then I've typed the notes, which we talked about, direction of most rapid increase and most rapid decrease. And the one is the direction of the gradient and the other is minus. So if you notice, the minus 1, 1 and 1 minus 1 are 180 degree opposite vectors. And if you notice the other page, this is using Maple to do partial derivatives, which of course we've talked about how to do, but I have some examples there that you could use as a reference if you were trying to work with Maple and wanted to do a partial derivative and forgot just exactly what it is you tell it. Well, what we will do Thursday next week is the 14.7 section, I think it is, the correct number anyway. It's using partial derivatives to find peaks and pits and saddles. Think of a surface like if you were flying over eastern Oregon or a place like that where there isn't a whole lot of brush. You can see volcanic craters, those are the pits. You can see volcanoes, those are the peaks. And then you have what you call a saddle, like a mountain pass. So if you have a surface as a function of 2 or more variables, then you can think of it in this way, that you can find where to locate the equivalent of a volcanic peak or a volcanic crater or a saddle by using partial derivatives. And it's actually pretty easy to do. It's easier, it'll be an easier class, say, than this stuff. So the light at the end of the tunnel isn't always the oncoming train. So have a good week.